Hello! In this video, we are going to prove the following theorem. Let a and b be real numbers, where a is greater than b is greater than 0. Then, for all integers n greater than or equal to 2, a to the n minus b to the n is less than a minus b times na to the n minus 1. Okay, now before we get to the proof, we are going to use the following fact in proving this. Given any two positive real numbers k1 and k2, if k1 is less than k2, then for all positive integers n, k1 to the power of m is less than k2 to the power of m. Okay, now let's get to the proof. To start, let's give ourselves two real numbers a and b, where a is greater than b is greater than 0. And from here, we want to prove that for all integers n greater than or equal to 2, this is true. And since we're trying to prove a statement about all integers greater than or equal to 2, let's use induction. So let's start with the base case. In the base case, we're trying to prove that this is true in the case where n is equal to 2. Meaning, we want to show that a squared minus b squared is less than a minus b times 2a. So let's start out by writing a squared minus b squared. Well, we know that a squared minus b squared is equal to a minus b times a plus b. And since b is less than a, it follows that this must be less than this, where all we did here was we replaced the b with a. Right? The reason why this must be true is because b is less than a, well, we can add a to both sides, so this must be true. But then, since a is greater than b, surely a minus b is greater than 0. So we can multiply the positive number a minus b on both sides, and we get this. And that's exactly what we have here. And we know that a plus a is equal to 2a. So as you can see, we have shown that this is less than this, which is exactly what we wanted to show. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to 2, where this is true. The whole goal of the induction step now is to show that this is also true for n plus 1. That is, we want to show that a to the power of n plus 1 minus b to the power of n plus 1 is less than a minus b times n plus 1 times a to the power of n. So really, this is what we want to show. And let's start out by writing the left-hand side. Now first, we are going to add and subtract a times b to the power of n. And from the first two terms, we can factor out an a, and from the last two terms, we can factor out a b to the power of n. Now, from our induction hypothesis, we know that a to the power of n minus b to the power of n is less than this. So, it follows that this entire thing must be less than this, where all we did here was we replaced a to the power of n minus b to the power of n with this. Right, and the reason why this is true is because, well, from this inequality, well, since a is positive, we can multiply the positive number a on both sides of the inequality. And then we can add this value to both sides of the inequality. And this is what we get. But this is precisely what this tells us. So yeah, we're good. And then what we will do here is we will multiply a and a to the power of n minus 1 together to get a to the power of n. And then we can factor out an a minus b from these two terms. And this is what we get. And now we're going to apply this fact. If we take K1 and K2 to be B and A respectively, well then we have that if B is less than A, then this is true. Well, B is less than A, so this is true. So we have that for all positive integers n, B to the power of m is less than A to the power of m. Well, if we take m to be our positive integer n, then we have that B to the power of n is less than A to the power of n. And since B to the power of n is less than A to the power of n, it follows that this must be less than this, where we just replaced B to the power of n with A to the power of n. And to see how we know for a fact that this is true, well, let's take this inequality and add na to the power of n on both sides. And then we know that a minus b is positive, so we can multiply the positive number a minus b on both sides of this inequality. And we get this. And this is precisely what this tells us. And now what we can do is we can take this parentheses and factor out an a to the power of n. If we do that, we get this. So we have shown that this is less than this. And that's exactly what we wanted to show. So this completes the induction step. And because we've completed both the base case and the induction step, this closes the induction. So we have shown that for all integers n greater than or equal to 2, this is true. And since a and b were arbitrary real numbers such that a is greater than b is greater than 0, this means that given any two real numbers, a and b, where a is greater than b is greater than 0, we have that this is true. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.